Okay, so good evening all, and thank you for joining this session. Today our 11th session, I think 10th session, 10th live session for the course welding processes, and so far we have seen all consumable and non-consumable welding processes, which involved mainly arc, right? And also in the last session, professor covered topic related to the high power energy processes, power beam processes, right? And professor taught about laser welding and electron beam welding, right? So if you remember, if we compare laser welding or any power beam welding processes with conventional uh, arc welding processes, then the main advantage for these power beam welding processes is narrow heat affected zone, and we can also uh, uh, do the joining of thicker plates, much thicker plates. In because of that, we can uh, uh, we can we can have advantage over the conventional processes, because in the conventional process we have to do multiple pass to join particular thicker plates, but in high power energy density processes, energy or power is actually concentrated to very narrow area, and because of that, power density of the process is higher, and it can ensure very large penetration, right? But if you remember that the examples what we saw, that energy density values for this laser beam and heat up arc welding processes is huge difference between the energy density value, right? And as energy density higher in the power beam processes, we can ensure larger penetration depth and very narrow fusion zone as well as heat affected zone. So uh, this process is very advantageous for joining thicker plates, right? And which causes lower distortion also, uh, compared to conventional welding processes, right? Conventional arc welding processes. But we have also seen that the narrow weld is also not good for proper distribution of the load, because load is not uniform over the entire or over the large area, so it is distributed on narrow region. So it is sometimes it is not good, because some kind of segregation is there at the center of the uh, uh, weld zone, and it will create a problem, right? And also we have seen the distortion problem is also minimum in case of higher beam welding processes, and we have seen this kind of plots, right? So in with the continuation of the last class, last live session, we can again try to see another power beam process here, like electron beam welding, right? So uh, and then in the next set of question, we will discuss about other welding processes, which are in the different category, like cast modification we can say, or another kind of pipe welding, mainly the process which is useful for pipe weldings, right? Which is magnetically impelled arc butt welding, right? And at the end of the session, we can again try to cover topic related to the some topic related to the welding metallurgy, because as when we move from solid arc welding, fusion welding processes to solid state welding process, we have to understand what are the disadvantages of fusion welding processes over solid state welding process, right? So before going to that, we will quickly recap what we have seen in the laser welding process. That in the if you remember, laser welding process, there is a great advantage is actually uh, the quickly start and stop of the process, right? And as also the energy is concentrated on very small area, uh, and by manipulating the actual energy which is uh, coming, uh, uh, we can ensure the full trade penetration, or we can also use this process as a in a conduction mode, just for a surface treatments, right, by reducing the power density. Okay. Or by reducing the focus area, we can say, in more better way, right? So we have seen, let's say in the laser welding, main thing is we can manipulate the process, and means any direction of the welding is possible. In other way, we can say zigzag welding is possible, right? Zigzag joint is possible. Okay. But uh, the main disadvantages what we saw here in the laser beam welding is actually, uh, though it is in the it is capable to do on any material in the open atmosphere, but another main disadvantage of it is actually the absorptivity of the photons, right? So some materials which are good reflector of the photons, so it will reflect the laser beam, right? So because of that, the efficiency of the process is not that much good on certain materials like aluminum alloys or silicon, we can say, right? So uh, this problem of photon absorption is actually overcome in the another power beam process, which is what we are actually discussing, like electron beam welding. Okay. So in this process, the main advantage over the laser beam welding is efficiency can be achieved up to 90%, because here we don't need the material to be good absorber of the photon. Okay. But again, electrical conductivity of the plates, or what we have to join, that is also important here, right? And another thing is, in the laser beam welding, we can even do any kind of shape or any kind of size of the specimen, but that won't be possible in the EBM sometime, because in the EBM, the main requirement of the process is we have to conduct the welding in the, under vacuum atmosphere, right? And if you remember that vacuum requirement, I think for this process is I think 10 raised to minus 3 to 10 raised to minus 5 atmosphere, right? And because of that, we can't kept all the specimen, or bigger size specimen under the vacuum, right? So it will need very large setup for that, right? So this because of that disadvantage, we can't use or manipulate the process for largest specimen. But again, in the if we consider energy beam density, then power beam density or energy beam density is higher in case of EBM process, electron beam welding, and because of that, we can ensure much deeper penetration than laser beam welding, and also means we can say even 15 to 20 centimeter plate can be joined in one single pass, right? If you remember, professor taught in the regular lectures, right? So uh, that is actually main advantage, and also uh, as we have also seen that the proper age preparation is also essential for this process, right? In case of electron beam welding, right? And in other words, the other characteristics like keyhole formation and all other things, they are same like a laser beam welding. Okay. So just to remember quickly that okay, so this is a typical macrograph for joint which is made by uh, electron beam welding. So we can see much thicker plate like 15 centimeter plate is welded in a single pass, and there are multiple passes we have to do to weld this much of thicker plate with the help of conventional GMAW process, right? So this right hand side for GMAW process. So As again, the basic of the process is same, that we have electron gun, and we have to give uh, supply, again, the cathode, means electron gun can be the cathode here, and it will emit the electron by certain principle, that why what we have seen in the first classes, like by thermoionic or field emission method, right? So once the electrons are emitted from the cathode gun or source, then it got accelerated with the help of positive voltage, accelerating voltage, and they are directed with the workpiece. But as we have seen, the workpiece and all this setup has to be kept in the vacuum atmosphere. So again, the investment cost or setup cost for this process is very high. Okay. And we always aid with the keyhole formation in this process, right? Because the energy density of the process is very high, and we have seen in the last live session also, and regular classes also, that which are the what are the forces which are actually responsible for the keyhole formation. Okay. So we have seen that, let's say in the left hand side, the beam pressure, we can say, vacuum pressure or recoil pressure, that will aid the keyhole formation, and which is actually balanced by surface tension force and gravity force, right? So we have seen in the laser beam welding also, PB is higher. Okay. But in case of EBM, electron beam welding, this beam pressure is very high. Okay. Because electrons are very tiny, and when they will hit to the workpiece surface, the KE of electron, because of lower mass, KE of the electron is higher, and it will convert KE to heat energy, kinetic energy to heat energy. So the uh, uh, and it is also concentrated on very narrow area. Okay. So that's why the beam and beam density in that particular location is very high. So we can say beam pressure is high, and also the interfaces which are actually subjected to the heat, they will immediately comes into molten state and will form the vapors, metal vapors. Okay. So when that vapors are try to escape, the recoil pressure of that vapor is also aiding the keyhole formation. Okay. So in the EBM process, the keyhole is always formed during the EBM process, and sometime if it is not controlled properly, like at the start and end of the process, because that keyhole has to be closed through the surface tension property of the liquid. Okay. So that's why it is necessary at the end of the process to control the characteristic of the keyhole formation, right? So otherwise it will end the throughout hole, right? Or at the end of the plate. So uh, uh, means the main pressure, we can say, is beam pressure, and again recoil pressure, which is higher in the electron beam welding, and which will always aid the keyhole formation. And that's why we can't use this process in the simple like conduction mode, what we has to done with the laser welding process, right? So these are simple questions which are actually related to the electron beam welding, what we have seen just now, that which one of the following force aid the QO formation in electron beam welding. So as I said, beam pressure or recoil pressure, that will always aid the QO formation, and there is no role of atmospheric pressure here, because we are actually doing the process in the vacuum, and gas pressure and difference pressure is not related here, right? So recoil pressure is the correct answer for first question, right? And also second question, they asked that what are the advantage of EBM over the LBM. So as we have seen that EBM requires very high vacuum, so it is again not the advantage, because we can't use very means a large size specimen, or that will also has to kept in the vacuum atmosphere, right? So this is obviously not a correct option, and or not a suitable option here. And in the second option, they said that very high process efficiency than LBM. Yeah, we can say it is advantage of EBM over the LBM because process efficiency is very high because the material won't actually reflect the electron beam, or it will absorb electron beam in better way compared to the laser, right? So in the laser beam welding, process efficiency is very low, but in case of EBM, process efficiency is high. So we can say B option is the correct one. Okay, and C and D option again it is wrong because EBM investment cost is lower than LBM, so it is wrong because EBM investment cost is higher, and also surface and interface preparation is minimal in EBM. So no, it is also wrong because we need proper surface preparation because we are melting very narrow area, and if there is any surface irregularities or any oxides at the interfaces, so that will trap inside, right? And because of that, it should be the proper surface preparation. Okay, and also we have seen typical vacuum values that we have to maintain during the electron beam process, right? So if you have any doubt related to the electron beam processes, then you can ask anytime in between, right? So sorry. Okay. Yeah. Okay. Mm, okay. Yeah, actually you are right. Actually this is for uh, just typical in order to perform EBM. The base suitable range is 10 to minus 3 to minus 1. But for more other sensitive welding application, we can use a vacuum range like 10 to minus 3 to 10 to minus 5. But it is not correct here. So the most use range in that vacuum range is 10 to minus 3 to 10 to minus 1. Okay. So thank you again for correcting. Yeah. So okay. So again, the next set of questions are related to the other welding processes like electroslag and MIA process, and also thermite welding, right? So maybe we will go one by one. Okay. So see electroslag. So again, it is a very important process for joining very thicker component, and we can say that again in this process the main striking principle for the heat generation is again arc, and then the heat is carried out through the electrical resistance of the molten plugs. Okay, so it is one kind of process which will end up with the cast microstructure, right? Okay. So just to quick recap, let's say in this uh, electroslag process, we'll have some backing plate or any shoe which can change its position, which is maybe copper, water cooled copper. Okay, and we'll have the plates or thicker plates that we want to join through electroslag process, electroslag welding process. So we'll have one filler material also, or filler rod. Okay, so that is inserted in between, and at the start we have to give power supply to this rod, and the component, right? uh, base base component. Okay, maybe it is just one cross section image, so we can't show here. So the mainly again the supply is again DCRP. So just quickly recap, DCRP again the polarity, where it's a reverse polarity, means electrons will travel towards the electrode and the more heat will be generated on the electrode. So it's as it is a consumable electrode. So again it is DCRP is the polarity we have to use, and we have to struck the strike arc between electrode and the workpiece, right? So once the arc is striking, the molten the flux is actually poured here, and again because of heating of the arc, this flux will go to the molten state, right? So heat will be conducted again, then the arc will be extinguished in that case, and heat will be conducted through the electrical resistance of this molten flux. Okay, and one slag layer will be always be there at the top of the surface, and as long as we are welding in the vertical direction, that layer will be go up and up, right? So again uh, this is again one kind of casting process where we are actually melting the interfaces with a very large volume. So obviously surrounding atmosphere or surrounding base material is again affected because of large amount of heat. So again we'll end up with a very wide heat affected zone, right? And again what I just said, that the arc is actually stuck between workpiece and filler material at the start only, right? And main process will be carried out through the electrical resistance of the molten flux. Okay, so with that maybe we can answer first two three questions. Okay, so in electroslack welding, arc is struck again. Arc is uh, arc is struck to first initiate the process and to create the molten slag, right? Or to melt the flux, right? And to form the molten slag over the flux layer, right? As slag density is lower than the molten flux, it will be float on the top of the surface, right? And again struck arc is struck to arc is a main heat source to cause the interface covalence. So it is a wrong option, because here arc is not a main source, it is just to initiate the process, right? And obviously arc is not uh, to melt the electrode, right? Though the output is melting of the electrode, but main our purpose is to create the molten slag. Okay, so sometimes in the process multiple filler rod can also be used if the volume of the flux has to be melt is higher, right? So maybe the C option is actually correct one for this question. And if we go for fifth question, the main heat source in the electroslag welding, again it is a electrical resistance of the molten arc, right? And electric arc between filler rod and workpiece, so it is not a correct way option, because it is just start of the process. They ask about main heat source, so electrical resistance of the molten arc is the correct answer. And for sixth question, electroslag welding is primarily used for welding of. So obviously this the large volume of the material has been melted at the interfaces. So it can be used for joining of very thicker section slabs, right? So B option is the correct for sixth question. Okay, and next two questions actually related to the again another kind of joining process, which we can't say it is coming under the exactly under the fusion welding process, right? So which is MIAP process. So it is a, we can say, magnetically impulsed right? So if you remember, we have already seen some processes for joining of pipes or tubes, right? Metallic pipes and tubes that we have seen, like flash butt welding and other welding processes like resistance offset welding, right? So this is also one of the process which is typically used for the joining of very thicker pipe cross section, right? So why it is so useful? Because another more famous process for joining of this is actually friction. Maybe we will see that in a couple of minutes. Friction welding, right? But in the friction welding, I think one of the component uh, uh, will be connected to the spindle, and this component itself is rotating. So there is some limitation for the size and shape of the component, right? And also the picture devices, right, to hold the component. But in the magnetically impelled arc welding, there is a simple uh, technique has been invented that to join this kind of thing is uh, by connecting magnet to the pipe that what we want to join, right? And because of that magnet, circular magnetic field will be developed, and because of as arc is stuck between the electrically carrying conductor, this arc will be start rotating because of magnetic field, right? And in the flash butt welding, if you remember, the arc will be stucking at only the circumferential surfaces where uh, the number of or resistance to the electrical path is less. Okay, so because of that, there won't be uniform melting of the entire cross section. But in case of MIAP process, as arc is rotating throughout the cross section, throughout the interfaces are actually in the molten state, right? And uh, once the interfaces is actually in the molten state, we have to give some upsetting force, and this entire flashed layer, or we can say molten layer, is actually flashed out again, right? And actually, as because of heating, the mostly the heat affected zone or partially melted zone which is present at the interfaces during the upsetting of the this another component, this partially melted zone will be covalence with each other with by mechanical covalence or mechanical deformation. Okay, so it is not completely like a fusion welding process, but again it is categorized in the fusion welding because at the start of the process we have to strike the arc, right? And interfaces are in the molten state at the start of the process, right? So so just we have already seen the videos that this is the image capture with the help of some high-speed camera which is placed inside the pipe, what professor showed. And this is actually the arc which is throughout the entire cross section, right? And these are the electromagnets or direction of the electric current and electromagnet. Because of electromagnet, arc will be in the rotating state, right? And This is again typical image of electroslag welding, what we have seen just few minutes before, that this is adjustable uh, uh, holder, copper shoes we can say. So once the cavity or welding of the interfaces takes place at the bottom section, this arrangement can be shifted toward the top. So again it is limited to the vertical direction only. Okay, and here we can see very good joint throughout the thickness of the, or thickness or circumferential cross section of the pipes, and we can join very thicker cross section also, right? So maybe we can answer these questions. So what is the main heat source in magnetically impelled arc bulk welding? Again it is a arc only, right? Because of arc, interface is actually will undergo in the molten state, right? And for eighth question we can say interface covalence in magnetic impelled arc welding is achieved. So again it is a B option is the correct one, as we have seen that once the uh, molten liquid form layer form on the interface, we have to give upsetting force, and the liquid will be splashed out, and the joint will be takes place in the semi-solid. It is not actually in the solid state, it should be in the semi-solid state, this option, then it will be more appropriate. So semi-solid state by mechanical deformation, or uh, yeah, so the B option is the correct one. Once the molten liquid is splashed out, we have to give the upsetting force, and because of mechanical covalences, uh, the joint will take place, right? So yeah, so I think with that I answered these basic questions about other welding processes. So anything you want to ask, sir, or you want to discuss here? Okay. So yes. No, no, actually it is not kind of a riser, so it is simply has to be done in the vertical position. Okay. So the next type of welding process is thermit welding. Okay, so if you remember, this is again one kind of welding where we are actually end up with the cast microstructure, right? So whenever we end up with the cast microstructure, we'll have very coarser grain structure, and also wider heat affected zone, because of heat is actually transferred to the surrounding area. Okay, and up to a larger amount of time, the substrate or the plates has to be joined. They are actually in the molten state or high temperature during the process, right? So this is also one kind of uh, the process where we end up with the cast microstructure, and mainly this process is developed for joining of rails, or you can say railways, uh, uh, because we can't carry any power sources, big size sources there, and to join the very thicker plate, right, of maybe magnesium steel or any other steel, right, which is used for the rails application. So in the remote areas, it is necessary to have this kind of joining process. And the main principle for this heat generation in this joining process is exothermic reaction. Okay, so let's say in the one of the example, it's a told that let's say if we consider iron oxide and aluminum powder, uh, which is also we called as the thermic mixture here. Okay, so aluminum is very active again in the powder form, right? Mainly again it is very kind of ignited, and once it is ignited with a certain uh, uh, material, mostly the magnesium powder, which is again very reactive. When the metal magnesium powder is sprayed over this thermite mixture, it will uh, act as a igniter, right? So uh, due to the reaction between this iron oxide and aluminum, uh, uh, aluminum oxide formation will be takes place, and this oxide formation is actually the exothermic reaction. So main heat will be uh, coming from this reaction. Exothermic means we can say that heat will be releasing, and whatever the element which is left over like iron from this reaction. So because of that leftover iron, because of that heat from the exothermic reaction, this iron is actually in the molten state. It will melt, and because of that, uh, the sufficient amount of liquid will be present at the interfaces, right? So it's kind of uh, uh, melting the metal, and then it is pouring in the cavities, right? Some dye will be kept on the rail surfaces, pre-dye, and that dye is actually pre-heated through the process like maybe generally gas weld, glass, what you can say, oxyacetylene flame. With the help of oxyacetylene flame, this joint has been preheated. The preheating purpose is not only just to preheat the die, but it is also reducing the temperature gradient of the interface as well as in the surrounding surfaces, so that there won't be any residual stresses or thermal stresses after that. Okay, or that will eliminate or minimize the effect of that, right? So uh, again, once the molten liquid is formed, it will actually poured into this die. Okay, and solidification will takes place, just, and it will form like a cast microstructure, right? So a certain treatment can be given after that, right, to improve the properties. So mostly this process is very helpful for joining of the rails, and also the reaction which is actually forming very high exothermic heat, we can say. So that also we consider as a copper, right, copper oxide. Okay, so uh, this in that exothermic reaction, heat generation will be maximum compared, even compared to the iron, right? So compared to the Al2O3 formation. So uh, just so if you remember that professor also suggested that during the lecture that in this iron, let's say, if we have to improve the properties of last cast microstructure, then we can add some certain element, certain ferroalloys, okay, in the thermit mixture itself, and also we can add certain fluxes like calcium chloride or other fluxes, which will form the slag and protect the process, right? And also we can add certain ferroalloys to improve the properties of or to have some desired properties at the final cast microstructure. And sometimes ferroalloys contain also carbon, and that it will again harden the joint. Okay, so there are certain things, and for that addition of that carbon, maybe generally will use steel chips or even graphite as a carbon source, right? So this is all for actually thermit welding, and then maybe we can try to solve the questions which are actually related to that. So the main heat source for aluminothermic welding is again, as I said, it is because of exothermic chemical reaction. Heat will generate because of that, and uh, the sufficient molten liquid is forming because of that heat generated or heat available at that interfaces, right? So the most common welding process used for welding the rails, again it is thermit. And which material is usually added to start the exothermic thermit mixture? So most of the cases, actually it is actually because of spreading of magnesium powder. Okay, and also in the 12th question, the aluminothermic welding mainly used for. So again it is again for rails as like iron also, and in certain cases copper also, because the exothermic heat which is actually generated because of exothermic reaction is maximum for copper, you can say. So I think with that I answered all basic questions related to the other welding processes. And okay, so all next set of questions are actually related to the solid state welding processes. We can say friction or any other friction based processes, right? So the second question actually related to the main advantage of solid state welding processes. So here, or maybe at the start of the friction state welding process, we can recap some question topic related to the solidification and equation cracking, right? So it is a welding metallurgy part. So uh, then we can take friction based processes or friction stir welding processes mainly, because actually uh, I have been working on the friction welding processes, so we can cover that topic in more detail in the next live session. So just for today, I will introduce what are the disadvantage of solid state welding processes, sorry, fusion welding processes. And uh, just for quick recap, I just want to tell here the main heating mechanism in the solid state welding process or friction based welding process, right? So again, for covalences of the material, or we can say in the joining of the interfaces, we need some certain amount of heat, right? So that heat, what we have seen in the other welding processes so far is because of arc or some other sources like resistance of the material. But in case of friction based processes, the mainly heat is generated because of friction, right? Okay, so kinetic energy of one moving part, if we rub on the other, then the Ke will be converted into the heat energy, right? So that is the main source of heat generation. And second one also, when one particular component actually rub on the another component. Let's say this is rod kind. Okay, so at the interfaces there are some certain kind of irregularities. Okay, or we can say asperities, and because of mechanical deformation, asperities, or we can say these irregularities are broken down, or in other words we can say because of breaking of the bond, that heat will be converted into the again heat energy, so that again source is, we can say, adiabatic heating. Okay, so these are the main sources of heat generation in case of friction based process, right? So the first friction based process what we have seen in the regular classes are friction welding, and that is again mainly used for joining up pipes, whether it is solid or in the uh, kind of tube type, we having internal and outer diameter. Okay, or else it can be of another shape like a flat rectangular plate kind of shape, or maybe any cutting tool, or that if we want to join, that can also be joined through friction welding process. And also some component, whether it is not in the rotating state, if in even linear movement is also sufficient enough to generate the friction at the interfaces and to form the coagulances by mechanical deformation, right? So the another difference we can say here is macro and micro deformation. So the process what we will be looking in the next live session is friction weld steel welding. So where we are actually using external tool, right, uh, for the uh, uh, for the material movement, or movement of the material at the interfaces. So it is kind of macro deformation, but here only at the interface the material is actually in the contact, so we can also consider it a micro deformation, right? So let's say in the friction welding, one component is stationary and one component is rotating, another component is rotating, and because of that friction will be generated at the interfaces by giving certain upsetting force start of the process, right? And once the friction is sufficient, heat generation will be sufficient, then the sigma y of the material will decrease and material will comes into the semi solid state. Okay, so after that we have to give final upsetting force in the linear axial direction, and the excess material which is got softened at the interfaces, that will come out as a flash, and the interface which are actually covalences with each other by mechanical deformation, right? So this process is widely used for joining again the pipe studs and even machine tools and other mechanical component. But in certain cases, suppose we can't have any proper picture, so that one component can be rotated on another, or components are very big itself, or maybe they are in the directly in the application, then we can have some certain kind of uh, uh, rotating ring type of thing, and because of that the other component what we want to join is actually stationary, and only this rim is rotating, and the friction will be generating at the interfaces of, because of that rotation of that rim, external rim, and heat will be generated, and it will cause the coagulances of the interfaces, right? So that called as a radial friction welding. So again uh, this is the process where upsetting force and initial stages is actually critical, and mostly uh, we should have to maintain the proper axial arrangement, right, of the both the component. Otherwise, slight variation in their axial arrangement, uh, the component won't be joined in the linear fashion, right? So uh, uh, with that, I think we can answer maybe first or two, one or two questions from this section. That what are the main parameters need to consider during the friction welding? So again, upset load obviously, and upset distance, that is also matters, right? How much distance we are upsetting, that much amount of flash will come out. Okay. So another variable is again rotation speed. Higher the rotation speed means higher kinetic energy, so higher heat or friction will be at the interfaces, so heat generation will be maximum, right? So the proper rotation speed should be needed, or higher rotation speed should be needed for the sufficient heat at the interfaces, right? So all of the above is the main parameters which actually generally used for friction welding process, right? The correct option is D option. And I think 14 and 16, 17 question we will discuss uh, again. Maybe we will start finish first related to friction welding. So friction welding interface covalence is again achieved by again it is solid state welding, or right, interface covalence is achieved by solid state, right? And another two questions are actually related to the friction star welding, that we will look, or we will see in the next live session. But for today, uh, we can again discuss some more about uh, disadvantages of fusion welding processes over uh, conventional solid state welding process, right? So so anything you want to discuss, sir, before that? Okay, just a minute. Okay, so as we have seen, the main principle about solid state welding process, there we are not uh, melting the interfaces, right? So the disadvantages of uh, fusion welding process, where we are actually melting the interfaces, are actually ruled out here in the solid state welding process. So if you remember what we have discussed in the fusion welding processes, that If a certain materials which are actually like stainless steel or aluminum alloys, wrought aluminum alloys, which are actually susceptible to the solidification cracking issue, right? So wherever the melting involved in the welding processes, this problem is more severe. So to join such a kind of alloys, mainly aluminum alloys, uh, uh, it is necessary to have certain process which don't have involve the melting, right? So this is again one advantage to join such alloys through the solid state welding processes, because it won't involve melting at the interfaces, right? So other issues like solidification related problems can be eliminated, right? And also in the solid state welding, we are not actually heating the metal up to the melting point, or not even in the close to the melting point. Okay, so it is generally above zero point 0.5 to zero point 0.6 of melting point. So the energy requirement of the process is also reduced, right? And also it is more productive or effective process compared to the fusion welding processes. Okay, and even sometimes we achieve very large size joint, or macro deformation is achieved in a single pass itself, right? So that is also one kind of advantage. And also we are not using any external pillar rod or pillar material, or any slag or any harmful compounds at the interfaces, right? So also we can say any inert gas medium. So because of that, this process is kind of clean process. And there are certain disadvantages like oxygen or porosity formation, uh, or hydrogen embrittlement problem. So there are so many problems related to the uh, gases which are actually entrapped in the fusion welding processes, that will ruled out here in the solid state welding process. So it's kind of clean process. And the only disadvantage of solid state welding process is actually the proper fixture and tooling requirement is essential, because heat is generating with the help of friction at the interfaces. So we have certain rotating parts which are undergone through the mechanical movement, right? So to hold that, proper picture and tooling requirement is essential, right? And also sometimes we have to prepare interfaces, or proper edge preparation at the interfaces, because we are not actually melting the metal, right? Or we are not adding external metal. So whatever is there, that will coalesce, and that will form uh, or fill the cavity at the interfaces, right? So there should not be any sufficient gap at the interfaces what we want to join through this kind of processes, right? And also the interfaces should be clean. There won't be any dirt or uh, dust at the interfaces. Okay, so these are the main um, overview of the advantages of uh, solid state welding processes over the conventional welding processes. Okay, so another thing, if we want to say about the weldability issues of the other materials through the fusion welding processes, then we have to consider certain example. So let's say if we consider the example of aluminum alloys or other alloys that we can discuss here to understand the main problems related to uh, uh, solidification issues, right? So let's say if we consider particular material for fusion welding processes, then what are the properties what we are looking in that material is obviously their melting point, thermal coefficient of expansion, thermal conductivity, and solidification rate, right? So the material which is having lower melting point, they are in one sense they are easy to join because of lower melting point interfaces. Low heat input is needed. Okay, and if their coefficient of thermal expansion is less, then the residual stresses or thermal stresses which is actually developed because of temperature gradient, that will reduce, right? And if material is having lower thermal conductivity, then heat will be contained in the material, right? So lower melting point, lower thermal coefficient of expansion, that should not be again negative and positive, it should be low, as close to zero. And also thermal conductivity, if it is low, and if the material don't have any solidification range, then let's say if the material which is having composition near to the eutectic point. So we will discuss that in the more detail, that what is the eutectic point and what is the role of large solidification range. So if the solidification range is narrow, then we can consider this material as a good weldability with the help of fusion welding process. Okay. And another way we can say the mechanical perspective, that the mechanical if sigma y is less of that particular material, then the actual residual stresses will develop, which is actually in the that uh, amount of residual stresses is actually reduced here if the sigma of material is less. And also if the material surfaces are not active that much, like let's say if we consider aluminum and titanium alloy, the materials are very active and susceptible to the oxide formation. So for those material or those processes, again we need extra shielding. Okay. So if the material is not active and have certain kind of physical properties, then they are actually good for fusion welding processes. But again, this is not the case always, because let's say if we consider aluminum alloys having lower melting point, right? So still they are actually difficult to join, because they have higher alpha, higher K, as well as in the wrought alloy specifically it has longer solidification range, right? So those, though MP and sigma y is less, aluminum can't be joined uh, with the effectively through the fusion welding process. Okay. So in other words, we can say aluminum is the material which is actually having higher liquid shrinkage. Okay. So let's say if we heat particular aluminum billet, and if we go beyond its liquid point, melting point, and if we start solidifying at from that point, so material starts shrinking, because solid have low volume compared to the liquid, right? So because of that, uh, uh, solidification shrinkage will take place, and that solidification shrinkage will be higher in case of aluminum. So in other way we can say, let's say if we have cavity of 50 of volume 50 cube, just for the example. So because of volume shrinkage, that we have to supply extra material, right, to achieve that particular volume of the final solid uh, plate, right? So we have to use a riser, okay, or in certain material uh, which are actually having good fluidity, let's say aluminum silicon alloy. In the aluminum silicon alloy, because of addition of silicon, fluidity of the molten metal will increase, and because of that, the metal which is actually in the last solidifying region, uh, that will actually creating the shrinkage, right? Because the obstruction is happening from the surrounding grain which are already solidified. Okay. So because of higher fluidity of the silicon, aluminum silicon, because of silicon addition, the interdendritic region melting point will be uh, uh, means the more amount of heat will be available at the interdendritic region because of silicon addition, because silicon having have higher specific or latent heat, we can say. So when it got solidified, it will release that extra heat, and because of that extra heat, molten liquid will be always be there at the interfaces or interdendritic region. So because of that, it will feel at the shrinkages whatever is forming, right? So it's kind of one kind of good if we add silicon for increasing the fluidity. Okay, but it has their own disadvantages. So just for the quick recap, I just want to tell uh, right? So I just want to say here what are the disadvantages of or what is the actual meaning of or what are the actual factors which are actually necessary for or actually contributing in the solidification cracking. So I will explain our here by taking the example of aluminum alloys, let's say. So mainly the aluminum alloys that are actually categorized into two major types like cast alloy and wrought alloys, right? So as I said again, the cast alloy which is having composition near to the eutectic point. What is the eutectic point? Here liquid is directly converted into the solids, right? So there is no solidification range involved. Okay, so there won't be any obstruction from the surrounding solidifier region, right? On the last solidifying liquid, we can say, because liquid won't be present at the interfaces. Directly, liquid will be converted into the solid phase. So most of the even in iron steels, we can say the category like cast alloy, like a cast iron. That's what the name itself, like a cast iron, which is having composition near to the eutectic point. Okay, so any alloy which is composition near to the eutectic point, they are actually very good for the casting application. Also, we can say welding application, because it won't involve any solidification cracking in those kind of alloy. Okay, but mainly the alloy which are actually strengthened by certain ways, by certain secondary processes, are not in the actual billet form. They are actually in the plate form or certain extruded rod. So that will definitely subjected to the secondary processes. Those alloy and having wide or larger solidification range, right? So those alloys can be categorized into wrought alloys, right? So in the aluminum alloys, we can say this is the sequence of wrought alloys, and also that wrought alloy, let's say there are certain elements which are actually having the major composition like copper in the 2 series, magnesium in the 5 series, manganese in the 4 series, silicon and manganese in the 3 series, and 6 series is mainly magnesium and silicon, 7 series zinc and magnesium, and 8 series is lithium, right? So these 2 series, 6 series, 7 series and 8 series wrought alloy actually the main strengthening factor in this alloy is actually precipitation, right? In 6 series precipitate like Mg2Si, strengthening precipitate, and in the 2 series it is Al2Cu, means it's intermediate forms, right? And in 7 series it's MgZn2 and Al3Li, can say in the 8 series. Okay, so uh, let's say if we consider only this mainly 7 series or 2 series, which are more prone to the solidification cracking. Okay, so why? Because that we will discuss again in more detail. So just for today, let's say the material aluminum series which is actually strengthened by the precipitate, right? And certain series which are actually strengthened by the work hardening, right? So that material is actually subjected to the different cold working processes, and because of that more dislocations will be generated, right? And this dislocation act as a resistant to the dislocation movement, right? Okay, so in other words we can say in the cold work hardened material or work hardened material, higher the dislocation density, higher will be the strength of the material and lower the ductility, right? So why I am telling this? Because let's say in the fusion welding processes we are actually melting the interfaces, right? And because of that heat will be transferred to the surrounding metals, surrounding region, and that that heat lead to the change of the initial microstructure of the alloy, right? Let's say if alloy is work 100, okay, so mainly the dislocation density will be higher in the base region, right? So because of that heat which is transferred to the surrounding region, this dislocation started annihilating, or certain processes like recovery and partial recrystallization, we can say, that will take place. In the center region there won't be any problem because here it is completely melted, right? So uh, the final characteristics can be depending on the last microstructure what actually we are forming, and that can be uh, monitored later also by adding certain inoculants or certain metals, certain master alloys that will refine the grain size of this fusion zone, okay. But for the material like aluminum alloys or rod product, in the surrounding region in heat affected zone, and material undergo dislocation annihilation, and because of that base metal properties will be decreasing, right? So obviously uh, 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 and also another strengthening of the aluminum alloys is because of precipitate. So whatever the precipitates are there in the uh, uh, inner fusion zone, that will simply dissolve because we are actually melting the metal completely, right? And they will nucleate back, renucleating by certain post-weld heat treatments, okay. But in certain cases the metal which is subjected near to the boundary of this fusion zone, which has a heat affected zone, their precipitate simply coarsen. They won't completely melt. If they are coarsen, there won't be extra solute available for renucleation, right? So again post-weld heat treatment is also not effective in such cases. So obviously all these issue can be avoided uh, uh, in uh, in solid state welding processes, because their heat affected zone is not that much significant, because we are not melting the center region, right? We are just heating that region up to certain temperature, right? So in solid state welding processes, what will happen in the center? In the center, though it is cold work microstructure, because of macro deformation in the solid state welding processes, the metal undergo a recrystallization, right? And dynamic recrystallization, because of dynamic deformation is happening during the process, right? And because of that, grain size is much finer, right, compared to other processes, fusion processes. So that is again one advantage, right? So of solid state welding process. And another thing what I want to discuss here is the issue of solidification cracking, right? So that won't be in the case of solid state welding processes. So I just want to quickly recap what is mean by solidification cracking, right? So so if you remember that uh, solidification cracking is more susceptible in the alloys which are actually in the having composition, broad composition, or solidification range is wider, okay. So how it is actually related here? So mainly what will happen during the solidification of the alloy, tensile stresses will be developed at the last solidifying region, okay. So that last solidifying region, definitely it is in the interdendritic region or intergranular, we can say, path, right? Because surrounding metal is already solidified, and because of that volume contraction will be takes place, okay. And the stresses which are actually acting because of that volume contraction, right? So uh, and also the thermal contraction will also be there at the uh, uh, because we are restraining the uh, uh, elongation of that material, or elongation of that particular zone, you can say, right? So these are two regions. Because of that, actually the material last solidifying region or intergranular or interdendritic region are subjected to the tensile stresses, right? And let's say if the material which are having large solidified range, there always be the liquid which is actually present here, right? Because here both solid and liquid phase is present, right? So as long as temperature is reducing, the amount of solid which is actually increasing and amount of liquid which is decreasing, okay? And always in the interdendritic region there will be the continuous liquid film which is actually forming if the material having rod composition, because have larger solidification range, right? So as I said, the stresses will act under last solidifying liquid. So if the continuous liquid film is present because of low melting eutectics, right? So as I said, uh, this material have some solid concentration, and those solids, let's say in the case of aluminum copper alloys, uh, right, or in case of even aluminum zinc magnesium alloys, there are certain eutectics, low melting eutectics which are actually presenting here at the near boundary. Why it is presenting at the interdendritic region? Because it is a property that when the material undergoes solidification, the solid will be solid content will be maximum at the interdendritic region or last solidifying region. So as because of higher solid content, it is possible that the eutectic phases actually forming at the interfaces or at the interdendritic region, and because of their low melting eutectic, uh, though the temperature of the surrounding is let's say 600, uh, uh, and low melting eutectic will be solidifying around 570, then still if the range of the material is around let's say 600 or uh, means more than 570, then obviously the material liquid film will be present there, because of these eutectic phases are not yet solidifying. So because of last solidifying region contain continuous liquid film, as well as tensile stresses which are actually developed because of volume contraction and thermal contraction, this liquid film won't undergo this liquid film undergo tearing, right? Because it won't sustain the load because of that tensile stresses, so it will undergo tearing. So mainly the solidification cracking will happen obviously in the higher temperature range, okay, or in the molten in the higher temperature range, and also the main reason is because of continuous liquid film as well as tensile stresses, right? So in order to avoid that, it is obviously necessary that we have to first use the composition which are near to the eutectic, okay? But in certain cases, let's say if it is not near to the eutectic, we have to add certain element so that this solidification range will be narrowed down, or the composition of the material will shift near to the eutectic, right? So certain solid elements that can be added uh, in the system, or to avoid or to avoid the formation of continuous liquid film. That means if we add very less solid element, then the continuous liquid film won't be there. Only small discontinuous packets of liquid will be there at the interdendritic region. But let's say if solid content is medium, then obviously that will be sufficient to form the continuous liquid film, okay? But if the metal, if we add extra solid atoms, suppose solid elements, that will shift the composition near to the eutectic, then means uh, we are having extra liquid at the interfaces, not the thin continuous layer, extra liquid will be there. So obviously whatever the tearing is happening, that tearing will be peeled out because of that extra liquid, right? So that is sometimes also called as a backfilling, okay? So obviously we have to select particular range of the solid concentration that will avoid the continuous film completely, or that will not allow the formation of continuous film which is not sufficient like here in first case, or else we always have extra solid atoms. It will form extra amount of low melting eutectic, as well as extra amount of liquid present at the continuous liquid film, and because of that, the whatever the crack is forming or tearing is happening, that will backfill because of that extra liquid. Okay, so that is a one kind of thing by controlling the composition or addition of the solid atom, right? So another thing can be done is by addition of certain element that will increase the surface tension of the liquid, right? So let's say in case of iron. Okay, let's say we are already aware that what is the properties of liquid. What is the surface tension? Surface tension is the property of the liquid surface which will avoid its shape change. Okay, or we can say in another word, it won't allow its surface to be changed, surface area to be changed, right? So in other words, we can say if the surface tension of the liquid is higher, then it won't form continuous liquid film. Instead of that, it will form the discontinuous packets of the material. Okay, so if the material is or interdendritic region, there are continuous, instead of continuous liquid film, this kind of discontinuous packets of the liquid is forming, then uh, uh, solidification cracking can be prevented, because here it is not a continuous liquid film, right? So the elements which can increase the surface tension of the surface tension of the liquid in the interdendritic region, then it will be very useful to form the discontinuous packets and avoid the continuous film of the liquid, and subsequently which will avoid the solidification cracking, right? So let's say in other way we can say also, let's say if we consider iron, where sulfur generally react with the iron and form the iron sulfides, and that will actually subset low melting phases that will present at the interfaces or interdendritic region, right? So instead of sulfur to compensate that effect, we should have to add certain amount of manganese. So instead of forming iron sulfide, manganese sulfide will be forming, and because of that, and this manganese sulfide having higher freezing range compared to iron sulfide, right? If it is a higher freezing range, means freezing temperature, means we can say it won't be in the liquid state for uh, 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 at a lower temperature, we can say, right? So this can be this things can be improve the or it will prevent the solidification crack. And another factor we can say here is grain size, right? So let's say if we consider uh, the material which is undergone columnar grain growth, right? Let's say this kind of, okay. So obviously this uh, uh, in this kind of region, it is more chances of formation of the continuous liquid film, right? So instead of that, if we have very finer grains, that means what, this grain boundary area is actually increased here, right? In that particular volume, in that particular volume, obviously solid fraction is same. Okay, so in that solid fraction, if multiple grains and grain boundary areas are there, so obviously solid will distribute at a certain grain boundaries areas, right? That means it will prevent the continuous liquid film formation. Instead of that, the film will form at a particular grain boundary areas, and that won't be that continuous, right? So obviously, instead of columnar grain, if we have equiax and finer grain structure, then it will be helpful to prevent the continuous film formation, liquid film formation, or in other word, it will prevent the solidification cracking. Okay, so certain elements that can be added in case of fusion welding processes. Let's say that we consider as an inoculant. Let's say so for aluminum alloys, mostly titanium is act as a nucleating agent. Okay, so if we add titanium aluminum in form of master alloys, so it will form Al3Ti, right? So this Al3Ti are uh, having certain relationship with the aluminum matrix. So this Al3Ti can be act as a nucleating agent for nucleation of those finer grains, right? So if there are sufficient number of Al3Ti particle, there will be more number of nucleants for the formation of the smaller grain, right? That means uh, higher will be the nucleation side, so finer will be the grain size, and the grain boundary area will be more in such a cases, and subsequently it will be good for avoiding the solidification cracking, right? So uh, in other way, other factor we can say, like residual stresses, that can also be minimized, like mechanical factors. Okay, and this residual traces can be minimized. Let's say if we have a particular of V joint, and if we want to join that through fusion welding processes, then obviously we should have to prepare let's say uh, concave geometry, sorry, convex geometry. Okay, instead of concave, that will actually reduce the amount of final stresses, or residual stresses we can say. So proper geometry, as well as thermal stresses also can be reduced, because we know that if we restrict the movement of or deformation, the friction thermal stresses will develop. So if we reduce the temperature gradient, okay, uh, then that thermal stresses magnitude will be decreasing, right? So to reduce the temperature gradient, definitely we should have to go with preheating, right? And in another way also we can say sigma y, if sigma y is decreasing, the residual stresses amount will be decreasing, right? So these are the other different factors which actually preventing the solidification cracking. Okay, so this is the just question from the last year course what I took regarding the welding metallurgy. That I was a TA there for the course. So this in this question they asked that the correct way to control the liquefaction. Just a minute. Yeah. So they said that the correct way to control the solidification cracking tendency in fusion weld is obviously, uh, as I said, the use of filler material that shift the weld material composition to a eutectic point. So obviously A option is the correct one. And we have to supply excess amount of solid which promote the terminal eutectic solidification. Yeah, that is also correct. If extra amount of liquid is available, then it will act as a backfilling of that tear out layer, right? And addition of element will decrease the surface tension. No, it is not correct, because we have to add certain element which can increase the surface tension of the last solidifying liquid, or liquid present at the interdendritic region, right? And also, as I said, preheating of the substrate can eliminate or decrease the temperature gradient, and subsequently it will decrease the amount of residual stresses or thermal stresses, right? So, and the fifth option they say use of the base metal with the coarser grain size. Obviously it is not correct, because we should have to use the metal which is having finer grain size to avoid the solidification cracking, because finer grain will have more grain boundary area, and will it distribute the solid element uniformly, and it will won't allow the continuous liquid film form at the intrinsic region. Okay, so I think first, second, third option is the first, second, and fourth option is the correct. So what I already marked here, right? So yeah, this is all about solidification cracking, and so I just want to say here what is the main difference that in solidification crack and liquefaction crack. Uh, let's say in the solidification crack, it will obviously happen at uh, it is sometimes visually macroscopically visible, and obviously as the liquid film is tear out, it will have smooth interfaces, uh, and it will generally happen in the fusion zone, right? uh, because that's the last solidifying region. But let's say another kind of issue like liquefaction cracking can also be take place in the case of fusion welding processes, mainly during the multipassing, right? Because in the multipassing, uh, let's say if we do the welding at the first pass, then metal at the interfaces will undergo solidification after the melting. But the metal, the or the area which is surrounded to that region is nothing but partially melted zone, or we can say heat affected zone. Okay, so still heat affected zone or partial melted zone temperature is higher. So if any low melting eutectic phases which are actually present at that interfaces, then that will undergo liquefaction cracking, and that will be more severe in the multipasses because instead of solidifying this partially melted region or heat affected zone in the first pass, if we are providing the multipass, then more amount of phases are actually in the liquid state, right? So because of that, this problem is more severe in the multipasses. So uh, just the difference is mainly it is actually happening in the heat affected zone or partially melted zone because of present of low melting eutectic phases. The reason is same, just these cracks are actually very small, and it can be visually or it can be observed only through microscopic observation, right? So what will happen that let's say if the material is solidifying, then the stresses will be acting uh, at in the last solidifying region, right? But if in certain cases, if the solidification of the fusion zone is takes place, and still there are certain amount of liquid which is present in the partially melted zone, then obviously stresses will be acting at the last solidifying region, means in the partial melting zone, right? And let's say in the aluminum copper series, Al to Cu is the mainly responsible for formation of low melting eutectic. Okay, so obviously stresses will be maximum that at a last solidifying region, so it will tear out or it will undergo liquefaction cracking in the PMZ or heat affected zone. Okay, so if we add certain element or certain filler material, let's say in case of aluminum, mostly aluminum silicon will be preferable. As I said, aluminum silicon having eutectic composition, or it will form low melting eutectics. Okay, so let's say uh, uh, if we add certain elements, so what will happen, it will solidify at the last because it has lower uh, uh, freezing temperature compared to molten aluminum, right? Lower freezing temperature, that means uh, uh, liquid will always be present at the last fusion zone uh, because of addition of this low melting phases, low melting filler material like aluminum silicon. Okay, so obviously the stresses will be maximum at the last solidifying region, means in the fusion zone. So that is a one of the way. So before solidifying the fused zone, obviously this will solidify yeah, like PMZ and HZ, and because of that whatever is happening in the fusion zone only, not in the PMZ and HZ. So this is the one way to uh, 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 minimize the liquefaction cracking, right? So I think the other reasons are actually same, like by reducing sigma y or preheating the substrate, that can also be possible, or with the grain size, finer grain size. So as I said, by to prevent the liquefaction cracking, the pillar metal that solidify before the partially melted zone, no, we should have to add certain pillar metal which will solidify after the partial melted zone. Okay, so aluminum silicon is a pillar we mainly use in case of aluminum alloys, that will that will ensure that last solidifying liquid will be in the fusion zone, not in the partially melted zone. Okay, so on the second option they ask that use of the single pass welding with higher net heat input instead of multi pass welding. So again it is not an option, correct option, because again higher heat input means what, it will have higher or higher width of heat affected or partially melted zone. Okay, so in we can avoid multi-passing, we can't avoid every time, but again use of single pass welding with higher heat input is again not a good option, right? So in the third case they ask that use of high energy density processes, obviously it is right, because it will reduce the actual heat input, or it will narrow down the partial melted zone or heat affected zone. Okay, so use of high energy density process can be one option, and another is preheating of the substrate. Yeah, that is always be the option, because it will reduce the temperature gradient, because temperature gradient will be different at a different zones, right? uh, let's say if this is heat affected zone and this is partially melted zone, then and if this is fusion zone, then temperature gradient will be different at a different zone, right? If you remember we have plot this, right? So this is like for fusion zone. So temperature subjected to high different cooling and heating rate, as well as uh, 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 different amount of temperature gradient as location is far away from the welded zone, right? So anyhow preheating is useful to minimize the temperature gradient, right, or subsequently minimizing the thermal stresses. And we can say use of the base metal with finer grain size, that always be recommended to avoid even solidification as well as liquefaction cracking. So third, fourth and fifth option is the correct one for seventh question, right? So I think these are the main thing I just want to discuss it here. Just a minute. Okay, so with that I think main advantage of solid state welding process, uh, obviously whatever we have seen just now, the problem of solidification cracking, uh, obviously all these processes are because of we are melting the metal, and to if we avoid the fusion welding processes, then obviously those problems can be avoided. So uh, as we are not even melting the metal in case of solid state welding processes, definitely heat input will be lower here. So that will be one kind of advantage over the fusion welding process. Also, absent of brittle solidified microstructure in the fusion zone. Yeah, that is also correct one, because let's say even if we use higher power density processes like electron beam welding or laser beam welding, again we have already seen that if there are some uh, intermetallic particles that will segregate at the last solidifying region, that will act as a crack nucleation sign, right? So obviously that kind of microstructure is or microstructural features are not available in case of solid state welding, because we are not actually melting the metal, right? And we are not actually solidifying at so the segregation effect is can be minimized here, right? Or can be completely eliminated, right? And for other advantage, we can say possibility to build dissimilar material. Yeah, that can also be possible. Okay, so nowadays there are different methods that will be very useful for joining dissimilar metal as well as in the solid state welding process. Maybe we will see that in the next live session, like processes like ultrasonic welding, even explosive welding. Explosive welding is mainly joining of entirely different microstructure, different material, like you can say copper, steel, aluminum, steel, something like that, right? So even in the friction based processes like friction stir welding, it is possible to join dissimilar materials, because in interfaces we are not melting, so the amount of intermetallic form, like mainly in case of aluminum and iron welding, the intermetallics are like Al3Fe. So that will still form in the case of friction welding processes, but that can be uh, minimized compared to fusion welding processes, right? So possibility, and also we have seen, let's say in case of resistance welding, if we use uh, different material, let's say this material having uh, high K, high thermal conductivity, and lower has low thermal conductivity, then obviously heat will be contained in the low thermal conductivity material, and nugget size or area will be higher in the lower plate compared to the top plate, right? So this kind of uh, uh, what you can say non-uniformity of the nugget size can be seen if we join two dissimilar metal with the resistance welding. So the case will be, and another case like for other metal will be same compared to solid state welding process, right? So I think with that we can mark all of the above answer in the 14th question. Okay, so this process actually friction state welding, that we will cover in more detail in the next live session, but just for preliminary information I can say here that FSW is mainly uh, or it's the ideal process for joining aluminum alloys. Okay, so we have seen that fusion welding disadvantages not there. Okay, because in the let's say in the friction stir welding, if we want to join two aluminum alloy plates, then we have to use certain external tool, right? And that tool is actually rotating, and that will create the friction at the interfaces, and heat will be generated at the interfaces, right? So obviously higher the rotation speed and lower the travel speed, heat generation will be maximum, because more time the tool is actually confined to that particular localized region, right? So heat generation will be maximum at that location, right? So the main heat generation is actually taking place by the help of some external tooling. Okay, so obviously the parameters are different. Means shape of the tool or shape of the profile of the pin which are actually inserting, also the travel speed, rotation speed, and what load we are actually giving, that all these factors are actually contributing here. Okay, and as I said, once the material is plunging in the interfaces, the material from one place is actually started going to another side, right? So I will tell that in the detail in the next session, which one is advancing, which one is the retreating side. So obviously material will flow from one side to another side. So here the only interface is not only uh, not only interface material is actually there at a joining place, right? So entire this material is actually processing, so it's kind of macro deformation. In other words, we can also say it's a bulk deformation, right? So uh, obviously if we give more load, right? So the heat generation will be maximum, because uh, friction value will be more in such a cases. So and also the material will be forged in that direction, because we are pushing that in the vertical direction, right? So that will also one kind of factor, like just I will list down here at rotation speed, travel speed, axial load. Okay, and these are the main factors. Among that also we can say these two are more related to the heat generation, and also there are other factors like can say tool hardness or tool material, we can say, right? Also uh, tool profile, here shoulder and pin profile. Okay, again thickness of the plate, that will also have certain influence, right? We can say plunge depth and thickness of the plate. Okay, so all these factors are actually responsible, and again nowadays this is completely automated process. So uh, there are certain factors like at what at the initially to gain the sufficient heat the metal sufficiently at the interfaces, will have certain dwell time. Okay, so that dwell time we can control, like we can give higher dwell time. Let's say if we want to join steel or titanium, we need more heat at the interfaces at the start, so that material will be sufficiently softened at the start of the process, and this surrounded material will be preheated, right? Obviously, so dwell time in certain cases is should be maximum at the start, at the end of the process, right? So that will also contribute for the proper softening of the material. Okay, so because as here we are softening the material, means what, if we are increasing the temperature at the interfaces, sigma y will be decreasing, right? Why sigma y is decreasing? Because we can say at a higher temperature multiple sleep systems are actuated. Okay, that means material will flow easily, there won't be any restrictions, and that's why the material will plasticize easily, just or deform easily. Okay, so in certain material, if heat is not sufficient, then we should have to preheat that material, so that there will be sufficient heat at the start of the process. Then we have to uh, 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 control with the by changing the parameters, right? So these are there are certain things that in the detail we can tell, we can discuss in the next live session about the friction stir welding, right? So I think for today's session we have covered welding metallurgy aspect also, and why we want to use solid state welding process over fusion welding processes for certain material, for certain specific applications. So that we have already seen in this live session. So if we have any particular doubt, then we can discuss it for some more time. Yes. Uh, no, actually, uh, it won't form any microporosity, but it will form certain defects. Let's say if we uh, if we won't maintain proper edge preparation, okay. Let's say if we cut the interfaces to be joined through the certain, like say hacksaw or something, right? Not with the precise machining processes, okay. Then it in that time means at that time the metal softened metal won't be sufficient to fill that cavity, okay. So that kind of defect will form, but microporosity it won't form, because metal is actually flowing significantly from one side to another side. So it will eliminate porosity. Even friction welding processes, friction stir welding processes can be used on the cast material to eliminate the porosity of the material completely. In certain material, if the porosity is very high, like macro porosity is there, so in such cases we can say in single pass it won't fill the complete porosity or complete cavity, but in the multi-passing it will modify the cast microstructure completely, and it will completely eliminate the microporosity. So but during the, because of process it won't form, it will eliminate the porosity, but process won't be prone to the porosity formation. Yes. Heat reflectivity means you mean to say in the friction stir welding? No, no, actually, for, yeah, yeah, no, no, it won't have any problem in the friction welding, because though the thermal conductivity is higher, I think sigma y or the aluminum is softened very easily, like even at 200 degrees Celsius for precipitation alloy. So there won't be any problem because of that, because sigma y is very less. Yeah. Yield stress, right? Yeah, if the metal is significantly softened at lower temperature, and in the friction welding or friction stir welding, if the temperature is more than even zero point 0.4 or zero point 0.5 of melting point, then it will be sufficient. Yeah. Yes. Yeah. Yes. Yeah. Initial upsetting force is just to confine the asperities together, right? So if it won't be fully contact to the interfaces, then heat generation won't be uniform. That's why we have to give certain force, but it should not be more, because at the start the strength of the material is higher. It is not in the softened state. So if we give large upsetting force, then it will actually buckle the specimen or buckle the workpiece. So that load is just to confine that complete cross section is in means it is in the interfaces. So it will cover the entire cross section. Just because of that, that small upsetting force will be there. Yeah. Yeah, we can say it is cleaning, but yeah, main purpose is to uniformly soften the material all over the cross section. Yeah. Sometimes age prepare. Yeah. Yes. So as I said, if there are some asperities are present at the interfaces, so that will flatten out. Means what it will flatten out because of breaking of the bonds, right? So as material is deforming from in the at the interfaces, the bonds will break, right? And because of that, that bond energy will convert into the heat energy. So that is nothing but adiabatic heating. Yeah. So are you okay with the explanation with the solidification cracking? Actually, I want, yeah, yeah, I want to take that at the last session, but it will be better because it has some good connectivity now because we just ended fusion welding. Yeah. Okay. So maybe at the start of the session, I think for complete 1 hour we can start with the friction stir welding. So if you want, I can take some references of the research paper, and I can also tell the actual mechanism of the joint formation and certain physics of the welding process. Yeah. Yeah, actually, yeah, they will say because they will say that because anyhow exam date is still very far, right? Around 28 maybe, something like that. So they will share that for 12th week. I think you can able to access these videos and these slides, right? That that can be downloaded, or it is just you can view that slides. No, no, not videos. This presentation slides also I shared, I think, right, through that Google Drive link. So it is there in the. Okay, 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 sir. So I will stop this recording for today's session. Then we will start next session with the friction stir welding processes in more detail, right? So again, once again, thank you for joining this session and for the discussion, right? So I will just stop. Yeah, I will stop the recording.